Good morning everyone. Welcome to the lecture series of Microprocessor. Today we are going to study the architecture of 8085. This topic is related to the subject Microprocessor with the subject code KCS 403, which is running in BTech second year as per AKGEC. And the students who are studying this subject are related to CSE branch, CSE IT branch, CSE DS and AIML students. So we know that 8085 is a 8-bit microprocessor and it is developed by Intel in 1970s around. It is a general purpose microprocessor that can be used in a wide variety of application, and the architecture of 8085 consists of several key components. First thing, it is a 20-pin IC, then it has an accumulator, 8-bit accumulator. First thing, we must understand that microprocessor 8085, it is a 8-bit microprocessor which states that we can process data, which we can process 8-bit data, and the result will be of 8-bit, which will be stored in accumulator. Whatever instructions we are going to execute, whatever operation we are going to run, its result will be stored in accumulator. So its result will be stored in accumulator. So your accumulator is an 8-bit register that contains the result of arithmetic and logical operation. Then we have some registers which are used to store data, and in case of 8085 we have 6 8-bit registers which are named as B, C, D, E, H and L. Out of these 6 registers, your HL behave as a default memory pointer. Whenever your memory operation is carried out, they will take the address from the HL register pair. So individually, if you want to use this register, each register can store 8-bit data, and we can use them as a pair also. BC register can be used as a pair, DE register can be used as a pair, and HL register can be used as a pair, so that we can store 16-bit data. Then we have the program counter, which is the very important part of the 8085 processor. It is a 16-bit register which holds the address of the next instruction to be executed. Then we have the stack pointer. Your stack pointer is also a 16-bit register which is used to manage the stack, which states that whenever we want to store some temporary data and which is needed during the time of execution, that data can be stored in stack also. Instruction register. The instruction register is an 8-bit register that contains the current instruction which is to be executed. Then we have the flag register. Flag register is also an 8-bit register which contains the status of flag, which indicates the result of the arithmetic and logical operation. So in this case, we have 8-bit flag register which states that whenever we do some calculation, if your result is 0, when we subtract 2 equal numbers, or whenever some carry is generated, or depending upon all these operations, some flag will be updated. And it is a dynamic register, and after each calculation, after each execution, your contents of flag register will be updated. Then we have data bus. The data bus is an 8-bit data bus which is used to transfer data between microprocessor and the memory, or between memory and microprocessor. So another one is your address bus. Your address bus is a 16-bit address bus that is used by the microprocessor, and with the help of 16-bit with the help of 16 address lines, we can access 2 raised to the power 16 memory locations. Then lastly, we have the control buses. These are single line buses, single bit buses, which is used to decide whether we want to read some data from the memory or IO devices, or we want to write some data on the memory. So this is the architecture of 8085 microprocessor. So we can see here that this complete unit is known as the register set, general purpose register set. It contains the registers BC register, DE register and HL register. Stack pointer, program counter which will be of 16-bit, increment and decrement latch register, instruction register, instruction decoder and machine cycle. And this side, on the left side of the system, we have this ALU which is used to perform arithmetic and logical unit, some temporary register which contains some W and Z register which are not accessible by the user. They are used by the microprocessor for the internal operation only. Then after the execution in this ALU part, the flag contents will be updated and the accumulator will store the result. The lower side of the block diagram contains the timing and control unit, which contains the supply unit, ground. 5-volt supply we must give to any IC, and ground, each voltage needs some ground voltage. So supply voltage and ground. We have clock frequency, clock circuit generator, which is connected between XN and X2. It is used to generate the frequency of 3 megahertz. Then here we have the control signals which are used by the microprocessor. The upper side of the section contains the interrupt control unit. We know that whenever we are running some instruction and we want some another subroutine to be executed, so that instruction will be executed and then microprocessor will transfer its control to the interrupt service routine, and then depending upon the priority, each interrupt has certain priority that we'll see in the later slides. Each interrupt has some priority, and depending upon the priority, that interrupts will be executed. This side of the section is known as the serial control unit, which is used to transmit data serially from the output, or if you want to transmit some data to the output devices. Here we have the address buses and multiplex address data buses. We know that from AD0 to AD7, these buses are multiplexed, and we can extract them. We can extract them by using ALE pin, and we can have address lines and data lines separately. So in the later slides, we are going to study the block, the working of each block. So first one is arithmetic unit. It is used to perform mathematical operations like addition, multiplication, subtraction, division, increment and decrement. Different operations are carried out in ALU. For example, different logical operation that can be if you want to shift some data, if you want to multiply some data, right, bitwise, OR operation can be carried out, bitwise AND operation can be carried out. Then flag register, it is an 8-bit register that stores either 0 or 1 depending upon which value is to be stored in accumulator. The flag register contains a 8-bit, out of which 5 bits are important and rest 3 bits are don't care, and maybe they can be used for the future purpose. The flag register is a dynamic register because after each operation it will check the result, whether your result is 0, positive, whether suppose you subtract one bigger number from the smaller number, your result should be in negative, right? So it will be updated in flag register. Similarly, if you want to compare two number, whether your number is greater than or less than or equal, then also your result can be checked in flag register. So we can say that flag register is a status register, and it is used to check the status of the current operation. And the 5 different flags which are used by the 8085, they are carry flag, parity flag, auxiliary carry flag, zero flag and sign flag. So let me draw the flag content. So we have the 8-bit flag register. T0, D1, D2, D3. Here we have carry flag, this is don't care, then parity flag, don't care, auxiliary carry flag, don't care, zero flag and sign flag. So this way we have the configuration of flag register. So carry flag, whenever some carry is generated, the value of carry flag will be 1, else the value of carry flag will be 0. Then we have parity flag. The parity flag will be set to 1 if you have even number of ones in a result, and if you have odd number of ones in a result in a 8-bit accumulator, so this parity flag will be 0. Auxiliary carry flag is set to 1 whenever some carry from the lower nibble to the higher nibble is generated. Then zero flag is set to 1 whenever the answer in the accumulator is 0. Suppose you subtract two numbers, suppose you subtract two numbers and the result is 0, your 0 flag will be set. And sign flag, if the MSB of your result is 1, it indicates that you have a negative result, and the sign flag will be set to 1. So next we have accumulator. Accumulator is used to perform input-output operation, arithmetic and logical operation. It is connected to ALU and the internal data bus. The accumulator is the heart of your microprocessor, because whatever instruction we are going to execute, one data should be placed in accumulator, and all the arithmetic and logical operations by default they work on accumulator, and the result will be updated in accumulator. So in case of general purpose register, in the first block diagram we have seen that we have some register arrays. So there are 6 general purpose registers. These registers can hold 8-bit values. These 8-bit registers are B, C, D, E, H, L, right? And these registers can store 8-bit data individually. And if you want to if you want to store some 16-bit data, we can use them as a pair: BC register pair, DE register pair, and HL register pair, right? Same way in the B register, higher byte will be stored, and in the C register, lower byte will be stored, and same process will go for the DE and HL register pair. Registers W and Z are temporary register, and they are reserved by the microprocessor. We cannot access them directly. It is reserved for the microprocessor for the internal operation. Then program counter. Program counter is a 16-bit register which holds the address of the next instruction to be executed. Suppose the current value of program counter is 4000H. It means that next instruction is at the location 4000H. So microprocessor will fetch that operation. And then the program counter will be incremented by 1, so that your microprocessor can go to next instruction. Stack pointer, it works like a stack. In stack, the contents of the register is stored in the that can be used during the time of execution. It is a 16-bit register, and the stack pointer is a part of memory, but the operation, we can randomly store data in the stack, whereas the program counter works in a random memory location. To use the stack pointer, we can use the instruction push and pop, and whenever we need to call some certain data or call some certain subroutine, we want to invite some certain subroutine, we use the call instruction so that can be initiated. And at the end of that call subroutine, we have to go back to the main menu also. So we use the return instruction. Then we have some temporary register. Temporary register, I have already told you that W and Z are the temporary register which are used during the time of operation. Then instruction register and decoder. It is a 8-bit register that holds the instruction code that is being decoded, and the instruction is being fetched from the memory. Then we have timing and control unit, the lower section of the block diagram. In case of timing and control unit, it is used to control the data flow between the CPU and the other peripheral devices. It can also be used to control the operation performed by the microprocessor and the device connected to it. There are certain timing and control signals like DMA signals. Under DMA signal, we can use hold signal and HLDA. The hold signal, whenever your DMA wants to send some data to the peripheral device without intervening of microprocessor, it will send the hold signal to microprocessor. Microprocessor will complete its current instruction which is to be executed. It will complete that execution and release its address buses and data buses. And microprocessor will send back the hold acknowledgement signal that now my resources are free, my address buses, data buses and control signals are free, and you can use my resources. Then we have some reset signal. Whenever you reset, microprocessor is reset, the content of program counter will be initialized to 0000H. Means from the starting your execution will be started. Then we have interrupt control, the top section of the block diagram. So whenever a microprocessor is executing a main program, if suddenly an interrupt occurs, the microprocessor shifts its control from the main program to that process, and after the request is completed, the control will be go back to the main menu. And there are 5 interrupt signals in 8085. We have interrupt, INTR, trap, RST 7.5, RST 6.5, RST 5.5. So depending upon the priority, trap has the highest priority and is the non-maskable. Non-maskable term states that we cannot postpone this interrupt. We have to execute this interrupt on the very first basis, on the very first time, and then microprocessor will go back to the main menu. Then after all these, 7.5 has the higher priority, then 6.5, then 5.5, and then INTR. Right? We can have software. These interrupts can be classified into 2 parts. One is software interrupts. These interrupts are hardware interrupts because they have the dedicated pin in the IC of 8085. There are software interrupts which are given during the time of assembly language programming. Then lastly, we have the address buses and data buses. Address buses and data buses are used to control the data flow between one part to another part. Right? Your data bus is a bidirectional bus and it carries the data which is to be stored. The address bus is unidirectional and it carries the location from where we have to store the data. So in 8085, the address bus and data buses are 2 separate buses and are used for the communication between microprocessor and other external devices. The address bus is used to transfer the memory address of the data that needs to be read or written, and the address we have 16 address buses, which states that with the help of 16 address buses, we can access 2 raised to the power 16, that is approximate 64 kilobyte memory location. Data buses are used to transfer data between the microprocessor and the external device, as well as we can have the external device as a memory or as a IO device. The data bus is a 8-bit bus which is used by the 8085 to transfer data at a time, and the data bus can also be used for the instruction fetch operation, where the microprocessor fetch the instruction code from the memory and decodes it. The combination of address bus and data bus are 8 data lines are multiplexed with the address lines also, and that can be extracted with the help of ALE signal. Then we have serial input-output control. This serial input-output control block is used when we have serial communication by using serial input data and serial output data pin. Serial input-output control in 8085 microprocessor refers to the communication of data between the microprocessor and the external devices. So we have the pins SID and SOD. Now let us check the flow of instruction in 8085. So whenever your microprocessor, we start the microprocessor, the execution will start from the program counter. Whatever address is stored in the program counter, the execution will start from that point. So it starts the program execution with the next address field, and it fetch an instruction from the memory location pointed by the program counter. For address fetching, for address fetching from the memory, multiplexed address data buses act as a address bus, and after fetching that instruction, this address bus will now act as a data bus, right? So we have these multiplex line, and when the value of ALE signal is 1, they hold these multiplex lines hold the address, and whenever the value is 0, they hold the data. So after data fetching, data will go to the instruction register. It will store the data fetched from the memory, and now the data is ready for the decoding. So for this, instruction decoder is used, and after that your timing and controls circuit comes into the picture, and it sends the control signal to the microprocessor and will tell the microprocessor that whether the given instruction is for read or write, or whether we want to work for the memory or IO devices. For this memory and IO devices, we have one dedicated pin. If the value of that pin is this pin is written as memory/IO bar. If the value of that pin is 0, your IO devices will be selected, means the communication will be done between microprocessor and IO devices. And if the value of this pin is 1, the microprocessor will use the memory. And hence, according to the timing and control signal pins, the logical and arithmetic operations are performed, and according to that data, the fetching from the different register is done by the microprocessor. The mathematical operations are carried out by the ALU. We must remember one thing, that if you add two numbers, one data should be placed in accumulator and one data should be placed, we can place that at memory, or we can place that in any general purpose register, that is your B register, C, D or E register. Right. So after performing the addition, that result will be stored in the accumulator. Your accumulator contents will be updated, and similarly your flag register will be will change its contents, and you can check the values in the flag register also. So, and with the help of serial IO data pins, that is SID, serial input data, and serial output data pins, we can send or receive input data to the external devices. In this way, your execution will be carried out. And if during the execution some interrupt is detected, microprocessor will stop its execution of the current process and invoke the interrupt service routine function, which will stop the current execution and do the execution of the interrupt service routine. It will complete its task and then it will go back to the main menu. Now let us quickly go back to the block diagram and check the working. So here we have the program counter, which will tell you that from where the execution is to be started. So, from that, your address buses and data buses will pick the address from the program counter, and the data whatever stored in these registers, that will be that data will be passed to the instruction register. Instruction register is a 8-bit instruction register. It will tell the microprocessor that whatever operation which operation is to be carried out, and that will be done by the instruction decoder. The instruction decoder, then it will pass the information to the timing and control unit, and then from timing and control unit, whatever read write operation, or whether we want to use IO or memory, that will be sent to the arithmetic and logical unit. So it will arithmetical and logical unit, one data will be placed from this side to accumulator. Some temporary registers will be used for the internal calculations. Then accumulator, with the help of this ALU, it will process some data, and your result will be updated again back to the accumulator. And if you want to store that data to some register, or you want to check some data in the accumulator, we can check the data in accumulator, or we can store that accumulator result to some another memory location, right? And during the time of execution, if some interrupt signal is generated from this part, interrupt signal is generated. Depending upon the priority, your interrupts will be handled. If your trap signal is high in the microprocessor, we have interrupt at trap pin, that will be executed on the very first on the very first time. And simultaneously, if you have RST 7.5, RST 6.5 and RST 5.5, suppose I have 3 subroutines and I have connected all the 3 subroutines to these pins. So depending upon the priority, RST 7.5 will be executed first. Then after that execution, RST 6.5 will be executed, and then after 6.5, RST 5.5 will be executed, right? So in this complete block diagram, finally we can conclude that it is divided into 4 sections. First one is your register array. We have general purpose register, which is BC, DE, and HL. Then we have special purpose register. Program counter, stack pointer are your special purpose register. Temporary register, we have this temporary register W and Z, and we have memory address register and memory data register also, which are used by the microprocessor, which are not directly accessed by us. Then we have special purpose register. Under special purpose register, we have ALU and accumulator and flag contents. Then timing control unit, second part is your timing control unit, which is very important and which is used, which operation we have to carry out. Then we have third is your interrupt signals, which is used to generate interrupt service routine, and the fourth part is serial control, which is used when we have some serial communication between the external device. This serial communication can be synchronous and asynchronous, which states that in case of synchronous, the frequency of microprocessor and the other peripheral device is same, and in case of asynchronous, we may have some different frequency, the transmission and the reception between some 2 different frequencies, right? So this is all about the block diagram of 8085. Thank you so much. For any query, you can contact us. Thank you.